Welcome everyone. My name is Mark Kurtz. I'm the machine learning lead here for Neural Magic, and today I'm going to walk you through something titled Pruning for Success. Before we get started, a few housekeeping items real fast. We'll be recording, or we'll be sharing the recording via email. Within 48 hours, it might be Monday when it goes out. If there are kind of any questions that you didn't get to ask or make any comments, please feel free. Use the hashtag #NoHardwareAI on social. And then obviously, please feel free to ask any questions at any time via Zoom's Q&A feature. So kind of talk over that. At the bottom, you should see a screen that looks like this. And real quick, just to kind of test it out, feel free to give it a try and tell us where you're calling in from. All right, we have one person calling in from New York City. We're actually out in based in Boston, so beautiful weather out right now. And then, oh wow, got somebody from Paris, Paris, France, Montreal, Canada, Longview, Texas, Baltimore. So definitely all over the world. That's awesome. All right. Let's go ahead and kind of dive in. Thank you guys for sharing. Definitely have a lot of people all over. So talking over pruning for success, and let's kind of dive into optimizing models for performance and cost savings. So one thing I want to start out with is that most weights in a neural network are actually useless. So what do I mean by that? Well, most of the weights in a neural network can actually be removed with limited to no effect on the loss, otherwise called pruning. So let's take an example. Let's take a fully connected network like we have here, right? So we have a few layers and then connections, weight connections in between them. What we can do is actually prune away a lot of those connections so that we get a not so fully connected network. And you can see that, obviously we've gone through and removed connections in between the inputs and outputs. So give me some real world examples. What does this look like? Well, for ResNet 50, we can actually get that to 90% sparse, remove 90% of the weights, and still match the baseline accuracy on the ImageNet dataset. For MobileNet, we can get that to 75% sparse and still match the baseline accuracy on ImageNet. So, talking over image classification, and we can dive into NLP a bit as well. So transformers, we can get those to 60% sparse and still match the 99% baseline blue score on the WMT dataset. And that's pruning both the embeds and the attention layers. Why is that useful though? Well, the big thing is that we can use that to get faster inference time. Going through an example real fast, about 4 years ago, I was deploying a ResNet 50 model for real-time examples, so batch size 1 on a 4-core CPU. We didn't have enough money to do GPUs and definitely did not have enough throughput to justify the GPU, so we were deploying on CPUs. Specifically, what we were trying to do was, as images came in, evaluate those images that users had uploaded and try and figure out if other users would actually like those images or not. So this was about 4 years ago. It took a few hundred milliseconds per image to run those. What that meant was that anytime we had spiking load, which usually we had a lot of, anytime a link would be shared, we get spiking load with that. It meant that we would back up, our queues would back up significantly. We wouldn't be able to get back to the user in real time. And even with multiple scaled up in parallel. So it had a lot of issues with that and had to do a lot of things to try and fix that, particularly through the pipelines. Today, though, we can look at a ResNet 50 example, and we can get into the tens of milliseconds per image. This is both through CPU upgrades in the implementations for CPUs, as well as for the software engineering, the engines that are running on top of this. For really good ones, like we have Neural Magic, running baseline dense, you can get to around 20 milliseconds per image. And then for others, TensorFlow and PyTorch in general get to around 50 milliseconds, 50 per image. But if we come in and prune that to that 85% sparsity, we can actually get to sub 10 milliseconds. So a 2x decrease over the dense time. And in general, we can actually get to around 7 milliseconds on some really good implementations. And what that means is that this is now actually just essentially a long-running function call and can fit anywhere in your pipeline that you may want it. Another big thing to talk over is reduction in size as stored on disk. So about 5 years ago, I was actually working on some augmented reality technology, and we were trying to deploy VGG16 onto mobile deployments. Specifically, we were looking at augmented reality and trying to detect walkable spaces in front of the user as we were trying to navigate them through, in real time, malls and shopping and airports, so we could navigate them to different stores, different items, stuff like that. Problem is that for deep learning, VGG16 being kind of the top one at the time, we couldn't fit it onto the mobile devices. And anything over, so it's prohibited for most edge deployments. Anything over 100 megabytes automatically requires Wi-Fi download for applications on iOS and Android. So it became completely prohibitive. So we actually were not able to deploy because of that. But if we come in and actually prune that model, we can get it to 11.3 megabytes, so 49x compression rate. And this is now both easily downloadable as well as can easily fit onto the device without any issue. And another thing to note is that most deployments are actually not taking advantage of this. So we did a survey with about 300 responses, over 300 responses to it. And one of the questions was, have you done any optimizations on your model specifically for production? And the majority said no optimizations. 24% said quantization, 22% structured pruning, 11% unstructured pruning, and 3% other. One note on that is that we do have the survey still live. So if you feel willing, please definitely fill that out, and we can get. We'd love to hear from you. And then also we have the survey results to date available on our blog. All right. Before we jump into the poll, I have one question I want to answer real fast, coming from Matt Phillips, and he just asked, "How does pruning help exactly? And if you zero out the weights, multiplication by 0 is still multiplication. Did you prune out whole layers? What happened to accuracy?" So we're going to definitely dive into this in a lot more detail, but just want to address that real fast. Is that whenever we're multiplying by 0, we can, if you're clever in how you do the implementation, you don't have to run those zeros, right? Because we already know the answer. So we can get speed up by doing that, by essentially just not running those ops. It's very tricky to do, but it's definitely possible. And then, so just pruning individual weights, not pruning whole layers. And then in terms of accuracy, we're still able to actually maintain the baseline accuracy by doing that. So definitely going to dive into more examples real fast. All right. And then I'd like to put up a poll and just see, if anybody in this webinar currently are actually doing any model optimizations. So let me go ahead and launch it now. And then feel free to answer. So obviously no optimizations. We also have quantization. So if you're going down to Int6, Int8, or sorry, Int16 or Int8 and doing that. Structured pruning, meaning that you're getting rid of channels or layers or filters within it. And then unstructured pruning, meaning that you're just getting rid of individual weights. All right, definitely getting a lot of responses. This is great. Let it go live for about 10 more seconds, and then we can share results. All right, 5 more seconds, and then we'll wrap up. All right, awesome. Let me go and end that, and then I'll share the results to you guys. So actually 67% currently in here doing no optimizations currently to the model. 18% quantization, 26% structured pruning. So definitely interested to hear more if you'd like to reach out on specifically what you're doing there for structured, and then 5% unstructured. So this somewhat matches our overall survey, which is always good to see. All right, thank you guys for filling that out. And so let's look at why a lot of people aren't doing any optimizations, specifically pruning. Well, one thing whenever we dove into that original poll was that that data science team size actually makes a big difference. So team size less than or equal to 10, only 6.7% had pruned in an unstructured way. Team size greater than 10, 18.8% have pruned. So what this says is that bigger companies and bigger teams have more resources to put towards this, and it actually takes a lot of resources in general to do this, both engineering hours as well as compute hours. But even then, it's still pretty low for the larger team sizes. And this is generally because systems have not supported unstructured pruning for speed up. So as I said before, where we're ignoring the ops that are multiplied by 0, so we don't have to run those. Systems have not supported that. It's again a very tricky problem. A lot of hardware implementations actually can't do it because of limitations on the hardware implementations. And then structured pruning actually severely limits the max sparsity that you can get out of that. So you can't get as much speed up whenever you're doing that if you're limited by the overall sparsity. And I'll go through structured sparsity in a second just to dive into that a little bit more. The other thing is that pruning takes a lot of learned intuition and iterations, and we'll go through an example and what that looks like. And then the other thing is that there's been lack of support and ease of use in general in ML frameworks. It's been kind of complicated to be able to define your own model or use pre-trained models and be able to sparsify those. So let's go over an example. So here's the unstructured model from before that we were looking at, and then let's compare that to a structurally pruned one. So they're both at around the same sparsity. So you can see for the structured pruned one, we removed whole channels out of that, right? So we got rid of whole channels in the layer. And what that did is it actually removed groups of weights together. And anytime we're doing that, generally that means that we're going to end up, we're making an assumption that we can get rid of all of those weights together. And in general, it doesn't work out because there's going to be some weights in there that were actually important to our optimization space. Oh, sorry, didn't realize I didn't have the structure there, but that's our structured comparison. All right, now let's look at actually pruning a network. Well, the first thing to note is that it's an iterative process. So we're going to start from a trained model. Over a number of training epochs, we're going to remove the smallest weights iteratively. So the weights that are closest to 0, we're just going to remove those from the training process. So this is what it looks like for, in general, for training a model, where we have on our y-axis the sparsity and our x-axis the number of steps that we've taken, so the number of batches that we've run through. And as we go through, we're going to iteratively remove weights as we're training. What this means is that as we're training, we can get rid of small groups of weights, the ones that are closest to 0, and then we can allow the optimizer to actually renormalize our weights for the new ones that are less important, right? So since we're changing the solution a little bit, we want to allow the optimizer a little bit of time to renormalize. And why does this work? Well, new research points to stochastic gradient descent actually being self-regularizing. So unused weights are naturally pushed towards 0, right? Deep learning networks are extremely over-parameterized. And the reason why it works so well whenever we're training these is that stochastic gradient descent is actually doing the regularization anyways. It's removing the weights that don't matter, but it's not setting them to exactly 0, and therefore we can't get speed up from that. So this means that unused pathways in the optimization space can be removed, and then the necessary ones are kept. And the ones that are unused in our optimization space are actually the ones that are closest to 0, and we can actually safely get rid of those. And then another note is that the proper sparsity can actually vary drastically per layer. Proper sparsity meaning the amount of sparsity we can get in a layer without dropping accuracy or affecting our loss. So this is going to depend on the size and properties of the layer, specifically how many channels are there, for convolutions, the kernel size, stride, all kinds of things. And a simple way to think about it is how much data is flowing through the layer versus how many parameters are available to act on that data. And then another part is that it depends on the overall architecture of the network. So, with NLP and in computer vision, there are really complex architectures that are being developed, such as, compression and expansion steps, attention mechanisms, all kinds of things. And those all have different sensitivities in terms of sparsity levels that can be set on them. So before we go any further, because we're going to go into the tooling in a second, we'd love to hear from you guys on what frameworks you're actually using and allow us to kind of, talk over which frameworks we support currently and possibly look at which frameworks we should be supporting. So we're going to make that live now. Obviously have the top ones, TensorFlow, PyTorch, and Keras in there, and then have some others like DarkNet specifically for the YOLO models, MXNet, and all kinds of things. All right, getting some good results so far. Let that go for about 10 more seconds. All right, 5 more seconds. Awesome, thank you guys. So I'm gonna go ahead and share those results real fast. So definitely majority TensorFlow. This matches, what we saw for in general for our survey, as well as PyTorch and some good adoption of Keras. Awesome, this is great. Thank you guys. And then let me go ahead and stop that, and then we can dive in to talking over, how can we make pruning easier? The first thing is that we need to simplify the hyperparameters. Whenever we're looking at pruning, there are a lot of hyperparameters. There's too many, meaning that in general, you're going to set try and decide how sparse you're going to make each layer, right? So for ResNet 50, we actually have 52 convolutions in there and one fully connected, and we have to decide how sparse to make every single one of those, right? So it's a lot of hyperparameters, and not only that, but we have to decide how many epochs to prune for and so on. So there's a lot of hyperparameters there that are tough to control. This leads to a lot of iterations and learned intuition that are required to actually find a workable solution, right? You have to try out multiple different sparsity levels, multiple different configurations to try and find something that actually recover. How can we simplify that though, right? Because that's not really a usable product for a lot of people. Well, the first thing is that we can actually build the intuition into an easy to use UI, right? So we can, within that UI, make recommendations and automatically try to figure out what the best sparsity profiles and how best to prune specific networks that are coming in. And we can, and what we're building in to power that is actually machine learning based technologies to help with that. We can also allow the user to edit further, specifically working on any learned intuition that they may have, right? So they might know how to sparsify the network a little bit better, and we can allow them to edit it further. And then additionally, we can constrain the choices based on the deployment environment. Depending on where you're deploying and the hardware, as well as different CPUs, can depend on what layers are actually going to give you the most speed up and what layers aren't going to be able to be sped up at all. Some layers are completely memory bound, meaning that any reduction in compute actually isn't going to help you, right? So that's not something that you need to prune, and therefore can save a little bit of capacity in the network and prune other layers a little bit more. So those are kind of easy to do big things. And then finally, kind of going through this UI, we can save everything to a simple YAML file, so that you can do easy continuous integration, continuous development. Right, do different runs and easily train this and save these as YAMLs into your source code or wherever it is, and have these ready to go as experiments, as well as fit in with any other ML pipeline you might be using. So let's talk over the UI. We're actively building this out currently. This is kind of the latest iteration on designs that we're actively working on right now, and a little bit of functionality built in. But you can see that essentially what we want to give the user is a global view of how sparse the automatic algorithms are trying to figure out how to make each layer, as well as how much speed up we can get overall on the layer, as well as how much time each layer is taking, both in the sparse case and in the baseline dense case. So overall, this quickly gives you information on where your network is taking the most time, and therefore where you can focus your efforts. And in addition to this, we're putting in sensitivities based on how sensitive each layer is to the loss function, as well as more complex things along those lines. All right, and then in addition to that, we're pairing this up with our NeuroMagic ML package. So current implementations are really cumbersome and require a lot of code. And what we want to do is simplify the implementations with easier to use interfaces. So let's look at simplified PyTorch training code, right? So just going over taking a model and optimizer, running it for a certain number of epochs and running the batches through that and training that, right? So a very simple PyTorch training code example. And then this is what the plugin for NeuroMagic ML looks like. So where we're actually able to sparsify a network. We just define our config path, set up a manager, and then we actually wrap the optimizer within PyTorch so that it can be fed through any training pipeline and you don't have to edit it at all. So that's essentially what that looks like. And I'm going to pause for a second because we do have a few questions coming in. First one is from Adrian Woolley, and specifically asking how much does sparsity in one layer impact the performance of other layers? Meaning that if we iterate on one layer, does this iteratively change the optimization on the others? So there is, to kind of dive into that, there is a little bit of complexity in terms of kind of covariances that are tied together between the layers. But in general, overall, it kind of works out to be a safe assumption if you don't assume those covariances, meaning that you can generally prune the layers individually without any effect on the other layers. Obviously, if you take that to an extreme and you cut out 95% of one layer, that's going to significantly affect the information bottleneck that's flowing through that layer. But if you do this iteratively, where we're cutting out only a few percent at a time, actually stochastic gradient descent, since it's self-regularizing, will redistribute over the entire network the parameters that are the easiest to prune and the safest to prune. So hopefully that makes sense. In general, as long as you're doing this iteratively, stochastic gradient descent really helps with regularizing and makes it pretty safe so that covariances don't have to be taken into account. If you're trying to do one shot, which is very, very theoretical right now, then you have to start taking in second order information like Hessian and stuff like that to figure out which ones are safe to prune. One shot meaning that we're not going to retrain after. And then we have two from Amandi Rathi. First one is pruning quantization. Is one better than the other in reducing inference time? And then specifically for UNet. So honestly, it's going to depend on your hardware implementation and where you're deploying at. But the nice thing is that pruning and quantization actually work well together as well. So whenever you prune a network, you might have to structure it a little bit to be able to take advantage of the quantization. But in general, you can actually work those together, and that's something that we're going to be actively coming out with in a release in a month or two. So we're actively working on that so that you can actually get speed up from both pruning and quantization together. And then how much value add does pruning plus quantization provide over just applying one of these techniques? So obviously with quantization, depending on the implementation, you'll get generally around 3x to 4x speed up. And then with pruning, you can get, honestly depends on batch size and all kinds of things, you can get anywhere from 2x generally to like 4x. So whenever you add in quantization, now you're looking at something that's on the range of 8x speed up. Obviously depends a lot on the data set, a lot on your deployment environment, but that's the kind of ranges that pruning and quantization generally pair well with each other to give even more speed up when you're running these. All right, and then another quick question was from another anonymous attendee, and asking, does this mean that your approach relies on the optimizer? What if you're not doing SGD? So the approach, all of these approaches rely on gradient descent, some form of stochastic gradient descent being used. Specifically that you're doing kind of standard deep learning training. But if you're using an RMS prop, Atom, just straight SGD, doesn't really make too much of a difference. And all the tooling that we built out can easily support essentially any optimizer that's running in any of the frameworks. All right, awesome. All very, very good questions. And then, so now let's talk over real quick, if we're not doing, if we don't have time to do pruning or don't want to work with it, let's talk over removing the pruning steps altogether. Well, the nice thing is that you can still get so essentially you want to get the benefits of pruning without any of the work. And the nice thing is that actually transfer learning works the same as it does for prune models versus unpruned models. And what this means is that we're actually constantly adding prune models to our NeuroMagic repository for this specific use case. So that you can easily come in, download a model, transfer learn onto it, and then be ready to run without having to play with any parameters. And then just a quick question that just came in from Matt Phillips. What model types does Neural Magic work for? Arbitrary CNNs, RNNs, any model I can define. So we have kind of two parts of the system. We have, the recalibration and ML tooling, and in general, that'll work for just about any model you can come up with. We're actively building that tool out to make sure that we support that out of the box, mainly because it's a little bit easier for us to do on the tooling side. And then if we're talking about the engine, which I'll show an end-to-end run of both in a little bit. If we're talking about the engine where we're actually getting speed up from sparsity, currently we're working with CNN, specifically image classification, as well as some object detection networks, general multi-layer perceptron type networks. And then on our roadmap, we're targeting segmentation, NLP, and RNNs and others. So we're actively building that out, and would be happy to discuss anything that you have going on there and how we could help try and speed that up or get it onto our product roadmap. All right, so let's go ahead and dive into a demo real fast. All right, so what I have here is just running on a desktop server that I have. And what we're going to do is actually just define a simple minced fully connected network. So specifically, we're just going to set up 5 fully connected layers with some ReLUs and batch color, and then prune that on the minced data set. So I have a previous train run that I already did, that we can see here. And on our validation data set, we got to around 98.6, 98.7 for top one accuracy. So that's the one that we're going to go ahead and load in. So we go ahead and run that. So we'll load that model in, load the weights, and then set up our data sets. And then let me walk you through creating a simple config. So the YAML file that I was talking over. So right now we're actively working on the UI to get it out to users. So in place of that, we have some simple notebook tools to be able to do that. So we just loaded the network. And for this, since I know a little bit about it, I'm actually going to set the first and last layers to 90% sparse, and then the other ones to 95% sparse. And this kind of comes from that learned intuition I was talking about earlier. But in general, what I'm doing is essentially pruning the layers that have fewer parameters, a little bit less than the layers that have more parameters. All right, so we set that up. What we're going to do is just save that config real fast. And then we'll use our tooling to go ahead and start pruning. So let me go ahead and kick that off. And we're going to run this on a GPU for training, just to get it pruned quickly. And what you'll see inside of here is a lot of PyTorch code. But the things to call out are, one, that we integrate with TensorBoard very easily. So we have other ways of logging, such as straight to your command line logs. But the easiest one that we found is TensorBoard Logger. So we use TensorBoard, set up, and then essentially we're just going to load from that config path that we just created, the config to tell it exactly how to sparsify the model. And then we're just going to wrap our optimizer. And once we wrap our optimizer, and again, this optimizer can be anything as long as it derives from the PyTorch optimizer package. TensorFlow is a little bit different, where we actually inject the ops into the graph. But yeah, as long as it's any kind of defined optimizer in PyTorch, it'll work with us. And then we're just going to kind of go through standard training ops. So let's look at where we're at. Okay, so we have about a minute and a half left, and then we can kind of look at our run that's ongoing right now. So what you'll see is that we're iteratively, for each of these that we defined, we're going to be iteratively getting rid of weights. So you can see that we're constantly climbing up. And what's actually happening is we're going to start pruning the layers, the weights early on. We're going to take bigger steps. And then as we get closer to the end, we're going to take smaller steps. And that's just because in general, there's going to be a lot of weights early on that we can get rid of, because the network's already self-regularized those to 0. as we get closer and closer to zero, or closer and closer to our end solution, we want to take smaller steps so that we're not deviating in our optimization space too much. All right, so that's going through. We're almost done pruning, so we're getting close to 90% for that one and close to 95% for that one. So let's take a look. Let me get rid of our baseline run. But let's take a look at what our accuracy is at. So we're bouncing around 98.6, 98.7, which is generally where we want to be. And sorry, this is using the atom optimizer for this one. All right, and we should be at about the top. Almost there. All right, just another 30 seconds that it'll go through. But what you'll notice is that we're actually able to recover very, very quickly. And in general, what that means, if we see this, so you can see that we're getting up to 98.7 now. So pretty much the exact same solution that we had with the dense mode. And what this means is that we actually could have pruned this more. And one thing that I want to call out is that if you're restricted on your deployment environment, specifically on latency or throughput constraints, you can actually sacrifice a little bit of the loss or accuracy if you wanted to get more performance. And this gives the ML engineer a lot more control around that versus the other option of trying to sub in a whole different architecture, right? So if ResNet 50, for example, won't run latency, instead you have to sub in MobileNet. Well, now you actually have a dynamic scale that you can pick from, and the ResNet 51 you can actually prune down to much better than a MobileNet solution, and still get to close to that same speed. All right, and then this should have finished up about now. All right, let me just double check. Okay, yep. So pruning completed, and then export the model, and then let's just check our end accuracy. So yeah, we got to 98.72. So actually did a little bit better than what we stopped with on our pre-trained model that we started with. All right, so now let's look at benchmarking. Let's look at, so now that we've used our tooling, what we're actually going to do is just export that to Onyx real fast. For the Neural Magic engine, we use the Onyx format to be able to run these. So we're just going to use that, and we're just going to benchmark and see what we get. So first, what we're going to do is benchmark the dense model, so the model before pruning, and then we'll benchmark the sparse one. So we're going to run the dense, and we get to about 6.26 milliseconds, and you'll see for the sparse, we got to 2.8 milliseconds. So over a 2x speed up on top of that. For larger models, obviously you can get more speed up as well. This is obviously a very small toy example, but for larger models, definitely can get more speed up as well. And then this was all at batch size 1024. All right. Awesome. So that was so that's the demo. I have a couple questions coming in. So let me go ahead and answer those. First one is from Simon Weedman. How much sparsity does one have to achieve in order to get real speedups when one applies unstructured sparsity? And how is the effect of unstructuredness on different platforms? Meaning, can CPUs benefit more from unstructured sparsity than GPUs? So both great questions. In terms of the first one, whenever we're looking at real speedups for unstructured sparsity, actually what we'll see whenever we look at these tests, for us, we start getting speed up around 50% sparse. We can start getting speed up for certain layers. And then in general, if you can get to anywhere around 80% sparse, that starts giving you some pretty significant speed ups. And it's actually a little bit, it's an exponential curve, meaning that, as you double, so going from 80 to 85%, you should get the performance, and 85 to 87.5% should give you roughly the same amount of speed up. So we're kind of exponentially increasing as we get closer and closer to fully sparse. And then looking at how does the effect of unstructuredness on different platforms affect it? Well, so one of the big things is actually to successfully run the structured sparsity as we do on for CPUs in our engine. Those codelets are actually too big to fit on GPUs onto their private caches as well as their implementations. So it's really, really tricky to actually get any kind of speed up on GPUs through unstructured. They can give speed up through structured, mainly just because, obviously you're just changing the matrix shape then, and anything gets speed up from those. But again, you're very limited by structured. There are some implementations that are starting to do block sparse. I don't know if you've seen it, but OpenAI pushed it, which is where you actually have huge blocks, like what was it, 16 by 16 blocks that you're removing to actually try and get speed up with GPUs. Again, because they can't really get down to the fully unstructured implementation, and that's just going to limit again your loss function, how much sparsity you can get to without affecting your loss. Next question from Rita Chadu. Sorry, I'm going to butcher this. Chado Padier, I think. But can we get the demo code? Yeah, absolutely. So we're actively sharing this with anyone in our beta program, and you can actually sign up for. I'll go through the link in a few minutes to share that out, so you can contact us, and we're definitely happy to ship that over, so you can run that on your environment and play with it. Next one from Simon Weedman again. And how useful is compression when one applies unstructured sparsity? One can attain really high compression ratios when one applies a lossless compression algorithm after pruning. However, at inference time, one has to expand it back to the original size, right? Yeah, so whenever we're looking at compression specifically and saving on size, this is specifically talking about the disk, savings on disk. So for example, if you have multiple models that you're trying to deploy for an application onto a user's deployment on the edge, that's where you start saving, is that you have 10 models there, and instead of taking up gigs, you can take up 100 megs for all 10 models. But yeah, whenever you're loading it into memory, you do have to fully expand. We had an anonymous attendee ask if we could get info on sparsity level. I'm not sure what that's referring to, but let me kind of talk over, whenever we're talking over sparsity levels, in general, what we mean, and let me go back to TensorBoard. In general, what we mean is that, so this is looking at the sparsity level. As we're going through in training, we're actively getting rid of weights within a network. And let's say that, within a layer. And within that layer, let's say that there are 100 weights in that layer. Essentially, if we get to 90% sparsity, then we're only going to keep 10 weights. So we'll have 10 weights in those 100 weights that are non-zero. All the others are zero. So that's what we mean by sparsity level. Another question from Arun Ramachandran. Is this sparsification via structured pruning? So we actually are going to be pushing out support for doing types of structured pruning in the event that you want to use the tooling for it. But this is all actually for, specifically what we're doing here is unstructured, mainly because, again, you can get to much higher levels of sparsity, so you can have a lot more, remove a lot more weights in the network whenever we don't impose structure onto the network. And then Matt Phillips says, sorry, did I understand that correctly? You do not get speed up when applying your pruning to a model running on a GPU. So it depends. For unstructured for fully unstructured, you're not going to get much speed up. There are some implementations that do runtime compression, runtime compression algorithms that try and get speed up, but they really don't get much speed up at all, maybe like 1.2x. There's some research papers out there on it, but nothing really in product implementations. There are a lot of structured approaches that attempt to do it. Specifically, one is just unstructured pruning, one is just standard structured pruning, where you're actually removing channels. And what that means is that you're just changing the dimensionality of the layers, right? So instead of having 1,024 channels, you'll have 900 channels in one layer, right? So that's something that everybody, any implementation will get speed up from. There is another implementation that does block sparse that came out of OpenAI. It was Fascinating. No, I think it was OpenAI. But they were doing essentially big chunks of weights, so 16 by 16 squares of weights that they're pruning away in groups, and then they can try and get speed up on GPUs. But in terms of support for fully unstructured, where you have a lot more availability and a lot more kind of higher ceiling to get to larger sparsity levels, then no, there's not really good support on GPUs for doing this. All right, awesome. Um, Can we go ahead and go back in and then just kind of share the final few things. So here's citations that I went through for the different sparsity levels and other things that I laid out in case you wanted to dive in deeper. Then in terms of next steps, well, feel free, as I said, to sign up for our early access program. That's how you can get access and actually run this code for yourself, run both the pruning, run the engine, see speed up on your models, all kinds of stuff. And please sign up at this link. In terms of live demo, we have some demos recorded and available on our website. And then can also obviously sign up to the early access program, and we can talk more on that as well. Feel free, as we said before, to take the deep learning survey. Obviously, just going to keep that open. We constantly share out the results to the community, so so very big on sharing and making sure this is available to everyone, and kind of helping drive our access. And then finally, if you want to learn more, send us an email at learnmore@neuralmagic.com. All right. Well, thank you guys for all joining in. I'll just ask if there are any other questions that anybody has that they want to know more on. All right. Awesome. Well, feel free to reach out. And thank you guys for listening. It was great talking to you guys.